Okay, let's go through questions 3 and 4 here. Starting with question 3, which says that we want to look at the double replacement reaction, 3.25 moles of barium fluoride with aluminum carbonate. So we'll start with the balanced barium fluoride, BaF2, plus aluminum carbonate, Al2CO3, which after a double replacement reaction is going to give me barium carbonate, BaCO3, and aluminum fluoride, AlF3. Balancing these isn't too bad. We might want to start with the aluminums. I have 2 aluminum on my reactant side, so a 2 coefficient here will give me 2 aluminum on my product side. Then I have a total of 6 fluorine here. So by tripling up over here, I get 6 fluorine there as well. Now I have 3 bariums in my reactants. Let's get 3 bariums in my products. That also gives me 3 carbonates, which luckily balances out my 3 carbonates here. So overall, this is balanced. And I can read that 3 units of barium fluoride react with 1 unit of aluminum carbonate to make 3 units of barium carbonate and 2 units of aluminum fluoride. Remember that that is just a true statement in general. It doesn't apply to any one particular chemical reaction. Just every time we do this chemical reaction, those ratios will apply. So now, let's look at this particular reaction where I told you straight up our measurement was 3.25 moles of barium fluoride. Right off the bat, I can say that that means that I'm going to end up with 3.25 moles of barium carbonate. Why can I say that? Well, because an equal amount of barium fluoride reacts as is produced as barium carbonate. There's a 3-to-3 ratio there. 3 units of barium fluoride make 3 units of barium carbonate, so an equal amount of barium fluoride and barium carbonate. In this particular case, 3.25 moles. Finding measurements for aluminum carbonate and aluminum fluoride is a little bit trickier. Let's use some stoich ratios. So let's start with the 3.25 moles of barium fluoride and use a stoich ratio that's going to take us away from barium fluoride and take us to aluminum carbonate. Based on our reaction, we see that that's a 1-to-3 ratio, based on the 1 here and the 3 here. So we multiply through, and we get our final amount of aluminum carbonate being 1.08 moles. I'll throw that up here, 1.08 moles of aluminum carbonate. It's a similar thing that we can do for the aluminum fluoride. If we start with 3.25 moles of the barium fluoride and use a conversion factor that takes us away from barium fluoride and towards aluminum fluoride, we can see in our reaction that there's a 2-to-3 ratio. So when all is said and done and we multiply through, we're going to end up with 2.16 moles. And we can write up here 2.16 moles of aluminum fluoride. And then you got 2.17, depends on where you run it. Okay, so we have all of this information now. I'm going to delete my conversions, although you should leave those on your page. I just want a little bit of space to finish up the question. I need to go back and find the molar masses, my capital M's, for all of these. Molar mass for barium fluoride, for aluminum carbonate, for barium carbonate, and for aluminum fluoride. You can do this in a couple ways. You can just Google it, or you can use your periodic table and start adding masses together. But when you do, you'll get the molar mass of barium fluoride is 175 grams per mole. The molar mass of aluminum carbonate is 234 grams per mole. The molar mass of barium carbonate is 197 grams per mole. And the molar mass of aluminum fluoride is 84 grams per mole. I've used 3 sig figs in all of my measurements here, just so that I get a consistent 3 sig figs everywhere I go. Okay, so now I can find the mass. In each case, to find the mass, I will just do number of moles times molar mass. So for example, 3.25 moles times 175 grams per mole, and that's going to give me a mass of 569 grams of my barium fluoride. Likewise, I'm going to get a mass of 253 grams of aluminum carbonate by multiplying here. I'm going to get a final mass of 640 grams of the barium carbonate and a final mass of 182 grams of the aluminum fluoride. Now, if we add these together, we see that the total mass on this side of the equation is 822 grams. And if we add these together, we see that the total mass on this side of the equation is 822 grams, confirming for us that our law of conservation of mass is holding in this case. Alrighty, on to the next guy. So here, we wanted to look at the complete combustion of C4H8, tetracarbon octahydride. In a complete combustion reaction, we know that we react with oxygen to form carbon dioxide and water as my products. Balancing this guy is pretty super straightforward. To balance 4 carbons here, I'll put a 4 here. To balance 8 hydrogens, I'll put a 4 here. In total, that gives me 12 oxygen on the product side, so 6 in front of my O2 on the reactant side gets me an overall balance. No big deal. Then, my measurement for C4H8 is that I'm dealing with 9.81 moles. I'm going to have a lot more of my carbonate and my water because I have 4 times as much carbonate and water as I have C4H8. So if I do 9.81 times 4, I'm going to get 39.2 moles of carbon dioxide and 39.2 moles of water coming out of this reaction. Even bigger than that, if I do 9.81 times 6, I'm going to get 58. I think I probably wrote this wrong, but I'm just going to go with it. I wrote 58.9 moles here. Oh, no, that was fine. Yeah, 58.9 moles of oxygen. Okay, so I have all these amounts. I can go and look up my molar masses, or even just calculate them. 4 carbons and 8 hydrogens is going to give me a total molar mass here of 56.1 grams per mole. Oxygen, I hope we're just kind of learning at this point, has a molar mass of 32 grams per mole. Carbon dioxide has a molar mass of 44 grams per mole. And water, a molar mass of 18 grams per mole. So now I can multiply through 9.81 moles, each mole weighing 56 grams, gives me a total mass of 550 grams of C4H8. 58.9 moles times 32 grams per mole gives me a total mass of 1,884 grams of oxygen. Although if we're keeping good track of sig figs, you'd want to write this as 1.88 times 10 to the third. Either way in this case is fine. Carbon dioxide, we multiply through 39.2 moles at 44 grams per mole. We get 1,724 grams. Although again, you might want to write 1.72 times 10 to the third grams. And then finally, our water works out to 706 grams of water. You might be off by a digit or 2 here or there. That's how this whole thing works. Don't fret that. What matters is that your total mass on this side, which for me worked out to be 2.434 grams, or 243 times 10 cubed grams, should be pretty darn close to equal to your total on this side, which for me worked out to 2.430 grams, but in scientific notation, That's also 2.43 times 10 cubic grams. Scientific notation did its job, and it got me 2 equal answers. If you got something anywhere close to this, 244, 242 times 10 to the third, you are in good shape. You know what you're doing. If you have any questions, let me know. We'll come back to this tomorrow. Thanks for watching.